Right now, this exact second, there is a real, physics-backed possibility that somewhere in the universe, a point no bigger than a subatomic particle has quietly decided to rewrite the rules of existence. Not explode, not collapse, rewrite. And from that single invisible point, a bubble is expanding outward in every direction at the speed of light, and everything it touches, every atom, every star, every galaxy, every possible thought, every version of you that ever existed, is not destroyed. It is unmade. Converted into a version of reality so fundamentally different that the concept of matter, chemistry, and life cannot exist inside it. You would never see it coming. No telescope could warn you. No satellite would catch the signal. Physics itself would make it impossible to receive any news from ahead of the wave, because the wave travels at the absolute speed limit of the universe. The first moment you'd know would be the last moment anything would be. That bubble might already be heading toward us right now. Welcome to false vacuum decay, and by the end of this video, you will never think about the ground beneath your feet the same way again. Before we get into what a false vacuum even means, let's talk about something you've always taken for granted without realizing it: the floor of reality. Everything you have ever seen, touched, or thought about sits on top of a foundation. Not the ground, not the planet, not even the atoms that make up the planet. Deeper than that, deeper than particles. There is an invisible ocean that fills the entire universe. Every cubic centimeter of empty space, every region between galaxies, every void where nothing else exists. And this ocean has energy. It has a shape. It has a level, like water in a bowl. And all of physics, every force, every particle, every law of nature you have ever heard of, emerges from the specific shape of this ocean. Physicists call this the vacuum. But they do not mean empty space the way you might. They mean the lowest energy state of every field that threads through the universe. To understand why that matters, you need to understand one deceptively simple idea. Energy likes to be as low as possible. Drop a ball, it rolls downhill every time, without exception, because systems always tend toward their lowest energy state. This is not a quirk of balls or hills. It is one of the deepest rules in all of physics. Everything in the universe is always, always trying to fall as low as it can go. Now here is the thing that should make your stomach drop. What if the universe itself is sitting on a hillside? What if the current state of existence, the specific configuration that allows atoms, molecules, planets, and brains to exist, is not actually the bottom of the hill? What if there is a lower valley somewhere, and we are just sitting in a shallow dip on the slope, held there by a temporary lip of rock, and one day, something will push us over the edge? That is the false vacuum. And this is not a fringe idea. This is not science fiction. This comes directly from experimental physics, from the mathematics that describes the most fundamental known structure in the universe, and from measurements made in one of the most expensive machines ever built by human civilization. To understand why any physicist loses sleep over this, you need to meet the Higgs field. You have probably heard of the Higgs boson, the so-called God particle that made headlines when it was discovered in 2012. But the boson itself is almost beside the point. The boson is just a ripple. What matters is the field it comes from. The Higgs field is an invisible field that fills the entire universe. Every point in space, everywhere, has a Higgs field value. And the particular value it has, the specific number it has settled at, is what gives particles their mass. Electrons are heavy because of how they interact with the Higgs field. Quarks get their mass the same way. Without the Higgs field sitting at its current value, every particle in the universe would be massless and would fly around at the speed of light. And atoms, and therefore everything made of atoms, could not exist. So the question becomes, why is the Higgs field at the value it is at? What determines where it settles? Imagine a ball rolling around in a curved bowl. The ball eventually comes to rest at the lowest point, the bottom of the bowl. The Higgs field does something similar. It settles at whatever value corresponds to the lowest point of its own energy landscape. Physicists call this the potential, a mathematical shape that tells the field where it wants to sit. Here is where the dread begins to crystallize. After measuring the Higgs boson with extreme precision at the Large Hadron Collider in Switzerland, physicists plugged the numbers into the mathematics that governs the Higgs potential. They calculated the shape of the bowl the universe is sitting in, and what they found was not a simple, clean bowl with one deep bottom. What they found was a bowl with two dips, one shallow, where we currently sit, and one far deeper, somewhere far away in the mathematical landscape. We appear to be sitting in the shallower dip. The deeper, more stable dip exists, and there is a real mathematical barrier between us and it. But barriers, in quantum mechanics, are not impenetrable walls. They are speed bumps. Given enough time, or enough of a random quantum fluctuation, a system can tunnel right through them. That word, tunnel, should alarm you, because it means the transition does not have to go over the barrier. It can go through it, like a ghost walking through a wall. Except instead of a ghost, it is the fundamental structure of space itself. Quantum tunneling is real. This is not a metaphor. It is not a fringe speculation. It is responsible for nuclear fusion in the sun, for the way transistors in your phone work, for radioactive decay. Without quantum tunneling, the sun would have gone cold billions of years ago, and you would not exist. Here is how it works, as cleanly as possible. In classical physics, the physics of everyday objects, if a ball does not have enough energy to roll over a hill, it simply cannot get to the other side. The hill stops it. But in quantum mechanics, particles do not have perfectly defined positions and energies. They exist in smeared-out states of probability. And this means that every particle has a small but non-zero probability of appearing on the other side of a barrier it classically could not cross. For tiny particles, this happens all the time. For everyday objects, a car, a person, the probability is so mind-bendingly small, it might as well be zero. But might as well be zero is not the same as zero. And when you are talking about the fabric of the universe itself, over timescales of trillions upon trillions of years, very small probability starts to look a lot more threatening. The Higgs field, spread across the entire universe, has a quantum probability of tunneling from the shallower valley to the deeper one. Because the field exists everywhere, this tunneling does not have to happen everywhere at once. It just has to happen at one point. One single quantum fluctuation at one location that manages to punch a tiny hole through the barrier. From that point, the new, lower energy version of the field spreads outward. That spreading is the bubble. Let us be very specific about what happens, because the detail is what makes this so extraordinary and so horrifying at the same time. At some random point in space, the Higgs field tunnels to its true, deeper ground state. The moment this happens, a tiny bubble of the new vacuum forms. Inside this bubble, the laws of physics are different. The Higgs field has a different value, which means particles would have different masses. Chemistry as we know it would not exist inside that bubble. The forces that hold atoms together would be reshaped. Everything that relies on the current laws of physics, which is everything, would cease to function. The wall of the bubble is where the old vacuum meets the new vacuum. This wall is not gradual. It is sharp, possibly at the scale of subatomic particles. As it passes through ordinary matter, it does not push atoms out of the way, or heat them up, or smash them together. It simply rewrites the rules at that location. What was an atom a moment before is no longer an atom after. The concept of atom stops applying, because the forces and masses that define an atom have changed. Now here is the part that breaks people when they really sit with it. The wall of the bubble moves at the speed of light. Not close to it, exactly at it. Because the energy difference between the false and true vacuum drives the expansion at the maximum possible speed allowed by the universe. Light takes about 8 minutes to travel from the sun to Earth. A bubble of true vacuum originating at the sun would reach Earth 8 minutes after it formed, and that is the best-case scenario for a nearby origin point. For anything farther, anywhere in the galaxy, anywhere in the cosmos, the math is simple. You have exactly enough time to be erased without warning. No message, no signal, no electromagnetic radiation of any kind could outrun the bubble, because the bubble is already traveling as fast as any signal can. The moment you could, in principle, know the bubble is coming would be the exact same moment the bubble arrives. There is no gap. There is no warning window. There is no grace period. What makes this particular end of everything scenario so uniquely unsettling compared to every other cosmic disaster, asteroid impacts, supernova, heat death, the big crunch, is the absence of drama. A supernova is spectacular. It is violent and bright and enormous. A black hole is dramatic in its own way. Even the heat death of the universe, though quiet, is a long, drawn-out fade. Every other cosmic catastrophe has a quality of eventfulness to it. Vacuum decay has none of that. It is the most violent event imaginable, the destruction of every atom in the universe, and yet it would be completely, perfectly silent from the perspective of anything it approaches. The people of a civilization 10 light-years from the origin point would live their lives, eat their meals, have their arguments, and dream their dreams for exactly 10 years after the bubble formed. Then, without any flash, any warning, any change in the night sky whatsoever, the wall would arrive, and the universe they inhabited would be gone. Not even the memory of it would persist. Memory requires atoms arranged in patterns. Atoms require the Higgs field to be at its current value. If the value changes, the atoms dissolve, and memory, and with it every record of everything that ever happened, is erased absolutely. This is not the end of a civilization. This is not the death of a planet or a galaxy. This is the end of the story. The end of all stories. And it would happen in silence. Take a moment with that. Before we move on, let us be completely clear about one thing. This is not fringe physics. This is not the territory of doomsday cranks or pseudoscientists. The possibility of vacuum decay is taken seriously by some of the most mathematically rigorous physicists alive. Papers on Higgs vacuum stability have been published in the most prestigious journals in science, authored by researchers at CERN, MIT, Harvard, and other major institutions. The topic was discussed openly following the Higgs boson measurements in 2012 and 2013, when the mass of the Higgs came back at a value that physicists describe as metastable, a word that means stable enough to last a long time, but not truly, fundamentally stable forever. Metastable. That word is doing a lot of work when it describes the ground state of existence. Stephen Hawking, in the preface to one of his books, noted that the Higgs boson's measured value could mean the universe is in a metastable state, and that it might one day undergo catastrophic vacuum decay, though he added it would take longer than the current age of the universe to happen. Probably. The word probably in that sentence is the part that stays with you. In part 2, we are going to go deeper into what the measurements actually say, and I mean the actual physics, the specific numbers, the calculation that physicists ran in the days immediately after the Higgs discovery. We will get into why the mass of a completely different, far heavier particle is the secret ingredient that tips the whole calculation one way or the other. And we will talk about what a bubble of true vacuum would actually do to you, down to the particle level, and why every other catastrophic end of civilization pales so completely in comparison that it does not belong in the same conversation. Stay with me. You made it to part 2, which means something in your brain grabbed onto what we talked about earlier and would not let go. Good. That is not paranoia. That is pattern recognition. Your brain is correctly identifying something genuinely unusual, something that most science communication does not quite hand you at full intensity. Let us go further in. In part 1, we established the basic structure of the problem. The universe sits in a false vacuum, a stable enough energy state, but not the deepest possible one. And quantum mechanics says there is a non-zero probability that it tunnels to the real bottom, sending a bubble of fundamentally altered physics racing outward at the speed of light. Now we need to talk about the numbers, because the numbers are where the really unsettling stuff lives. July 4th, 2012, Geneva, Switzerland. Inside CERN, the European Particle Physics Laboratory built under the French-Swiss border, two independent teams of thousands of physicists announced that they had found the Higgs boson. The champagne was opened. Peter Higgs, the physicist who first proposed the particle's existence nearly 50 years earlier, cried in the audience. But even as the celebration was happening, some physicists were already running the calculation that would haunt everything that came after. Here is the thing about the Higgs boson discovery. The number that mattered was not just that the particle existed. Physicists had been confident for decades that it existed. What mattered was exactly how heavy it was, its precise mass, because that number directly encodes the shape of the Higgs potential, that mathematical landscape we talked about in part 1. The mass came in at approximately 125 giga-electron volts. Write it down. That number is the hinge everything else swings on. To understand why, you need to know something about how quantum physics actually works at the level of fields. The Higgs potential, the shape of the energy landscape, is not a fixed, static thing drawn once at the beginning of time. It gets corrected, order by order, by the quantum fluctuations of every other particle in the universe. Virtual particles pop in and out of existence around the Higgs field constantly, and each one nudges the shape of the potential slightly. Most of those corrections are small, but one particle gives the Higgs field a correction so large that it dominates everything else. The top quark. The top quark is the heaviest fundamental particle we know of, roughly 173 times the mass of a proton. Its mass is enormous by particle physics standards, and because of the way the Higgs field and the top quark are mathematically coupled, the top quark's quantum correction to the Higgs potential is massive. It does not just nudge the shape, it fundamentally alters the depth and position of the second, deeper valley. Put the top quark mass and the Higgs boson mass together in the calculation, and you get a precise answer. Which valley is our current vacuum in? Is the barrier between the two valleys so high that tunneling is essentially impossible, or shallow enough to allow it? When physicists ran that calculation in 2012 and 2013, using the best available values for both masses, the answer that came back was deeply uncomfortable. The universe appears to sit in the metastable region, a zone where the second, deeper valley genuinely exists. The barrier between the two is finite and crossable, and our current vacuum is not the lowest possible energy state. The universe is stable, but only because it has not had bad luck yet, not because it is sitting safely at the bottom. The boundary between genuinely stable and metastable cuts almost directly through the region where our measured values live. Adjust the top quark mass upward by a few percent, well within the measurement uncertainty, and the universe is comfortably stable. Adjust it downward by the same amount, and the calculation suggests the vacuum is outright unstable and should have already decayed. Right in the middle of that uncertainty range is exactly where the measurements land. Some physicists look at this and see a coincidence that demands explanation. Others look at it and see a warning that the calculation is not finished yet, that new physics, new particles beyond what the LHC has found so far, might shift the result and place us safely inside the stable region. Both responses are scientifically legitimate. Neither one makes the central result go away. As of everything we know right now, the best calculation available puts the universe in a false vacuum. Here is the part most people get wrong when they first hear about this. Vacuum decay is almost certainly not something to worry about on any human timescale. Let us be completely honest about that. The best estimates from current physics put the rate of vacuum decay, the probability of a spontaneous tunneling event per unit volume of space per unit time, at an absurdly tiny number. When you integrate that rate over the volume of the observable universe, and ask how long you would expect to wait before a decay event happens anywhere within it, the answer comes out to roughly 10 to the power of 400 years. That is not a large number in the everyday sense. That is a number so far outside human intuition that no analogy quite captures it. The age of the universe is approximately 14 billion years. 10 to the 400th power makes 14 billion years look like a single heartbeat in the history of the cosmos. For comparison, the stars will burn out in a few trillion years. Protons, if current theoretical predictions hold, might decay in 10 to the 34th power years. Even that towering number is cosmically close compared to the vacuum decay timescale. You are not going to lie awake tonight worrying about this. No one alive, or anyone likely to be alive for any imaginable span of civilization, will witness this. But, and here is where the real discomfort lives, stable for an unimaginably long time, and actually fundamentally stable are not the same thing. A glass balanced on the very edge of a table might sit there for decades if the room is quiet. You would not call it stable. You would say it is waiting. The universe, according to these calculations, is waiting. The rate is tiny, but the rate is not zero, and a rate that is not zero means an outcome that is not impossible. Timescales make it irrelevant to us personally, but they do not change the category of thing we are in. The other thing the calculation gives you is not just a rate, but a mechanism. Physicists Sidney Coleman and Frank DeLucia worked out in 1980, more than 3 decades before the Higgs was even discovered, the precise mathematical description of how a bubble of true vacuum nucleates and grows. The Coleman-DeLucia calculation gives you the shape of the bubble at the moment of nucleation, the energy released as it expands, and the exact profile of the wall as a function of the fields involved. This is not hand-waving. It is a specific, testable mathematical framework, sitting ready to describe an event we hope never happens. What it tells you is that the nucleation point, the location where the transition begins, is a sphere of true vacuum about 1 Planck length in radius at the moment of formation. 1 Planck length is 10 to the minus 35th meters, a scale so tiny that no physical process we can measure comes anywhere near it. From that invisible seed, the bubble expands, and it never stops. Imagine you are standing somewhere, living your life, and the bubble wall arrives. What physically happens? The answer is nothing that your body would register as a process. There is no heat, no radiation, no impact, no shock wave you would feel an instant before. The wall is a boundary in the Higgs field's value, a location in space where, on one side, the Higgs field has the value it currently has, and on the other side, it has a different value. As the wall passes through you, every particle in your body instantly finds itself in a universe where the Higgs field is different. The masses of particles change, the strengths of forces change, the specific configuration of the electromagnetic force, the force that holds electrons in orbit around nuclei and makes chemistry possible, would be different. The atoms in your body would not explode or combust. They would simply stop being atoms in any meaningful sense, because the rules that define what an atom is would no longer apply. This is not like being vaporized. Vaporization is actually a very gentle process by comparison. You are still made of atoms, just disconnected ones. What happens here is more like being made of words in a language that the universe no longer speaks. The letters do not burn, they simply stop meaning anything. Every structure, every pattern, every arrangement of matter that has ever meant something, a cell, a brain, a solar system, a galaxy, passes through the wall and emerges as a structureless arrangement of whatever kind of stuff can exist in the true vacuum. The universe on the other side of the wall is a locked room we can never look into. What we can say is that everything on our side is gone, in the most absolute sense of the word gone that physics allows. This is the question that turns this from an abstract cosmological curiosity into something that feels personal. The honest answer requires some care, because a careful answer is very different from a scary one. The mechanism for vacuum decay, in the standard picture, is a random quantum fluctuation. It is spontaneous. It does not need a cause. It does not respond to human activity. It either happens at random, somewhere in the universe, or it does not. And no human action, no accelerator, no experiment we could ever build in any plausible near or medium-term future comes within many orders of magnitude of affecting it. The Large Hadron Collider, the most powerful particle accelerator ever built by human civilization, a machine 27 kilometers in circumference, drawing enormous amounts of power, smashing protons together at collision energies that were once unimaginable, produces collisions at energies that are something like 10 to the 15th times smaller than what the theoretical barrier for vacuum decay would require to be crossed deliberately. That gap is not an engineering challenge. It is not a budget problem. It is so vast that it removes the question from the domain of human responsibility entirely. The most compelling piece of evidence for this comes not from our machines at all, but from the sky. Cosmic rays, high-energy particles arriving from deep space, slam into Earth's atmosphere constantly, at energies vastly higher than anything the LHC produces. The most extreme cosmic rays carry kinetic energies 100 million times greater than the LHC's top collision energy. These events have been happening not just on Earth, but throughout the entire observable universe, on every planet, in every atmosphere, on the surfaces of neutron stars, in the environments around black holes, for billions upon billions of years. The universe has been running particle physics experiments at energies we cannot dream of matching, constantly, since long before our solar system existed, and the false vacuum is still here. That is not a coincidence. That is data. It tells us that the vacuum is stable against exactly the kinds of high-energy events that our technology could ever plausibly produce. The conclusion is clear, and the physics community is settled on it. Current experiments, and any experiment conceivable on human timescales, pose no threat to vacuum stability. The question belongs to cosmological timescales and natural quantum fluctuation, not to anything with a power switch. There is another dimension to this story that most people never reach, and it reframes the entire picture in a way that is simultaneously stranger and, depending on how you look at it, almost comforting. In modern cosmology, a well-discussed theory called eternal inflation suggests that the universe we live in might not be unique. During the first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion, inflation, that solved several major puzzles in cosmology and is supported by multiple independent lines of observational evidence. But in the eternal inflation extension of this picture, inflation does not just happen once in our universe and stop. It continues in an enormous background, with different regions constantly inflating and pinching off into new pocket universes, each with potentially different physical constants and different Higgs field configurations. In this framework, and I want to be clear that while this is taken seriously by many cosmologists, it remains theoretical and contested. Our universe is one bubble among an enormous number of bubbles, each embedded in the inflating background. Different bubbles could have different Higgs field configurations. Some would be in true vacuums. Some would be in false vacuums that decay quickly. Ours appears to be in a false vacuum that decays very slowly. Or, if we are lucky, one that the calculation will eventually show is actually stable. Here is where it gets philosophically strange. In some versions of this picture, a vacuum decay event does not just erase a universe, it creates one. A region of false vacuum that tunnels to a true vacuum could, under certain theoretical conditions, give rise to a new pocket universe inside the true vacuum bubble. From our perspective, it is catastrophe, physics rewritten, everything gone. But from inside the new bubble, an entirely new Big Bang might unfold. A new cosmos with its own laws, its own matter, its own possibility of structure. That does not make the end of everything less final for us. It does, however, change what the event means at a larger scale, from a tragedy to a transition, from a deletion to a transformation. How much comfort that offers is entirely a personal question. One more thing before we close part 2, and this is the one that stays with people the longest. The probability of vacuum decay at any given location in space, at any given moment, is extraordinarily small. But probability and space are a dangerous combination, and here is why. If the universe extends far beyond what we can observe, and all current evidence is consistent with that, then somewhere in that vast expanse, every possible event with a non-zero probability is either happening now or has happened. The region of the universe we can see is not all there is. Light from the Big Bang has had roughly 14 billion years to reach us, which means we can only observe a sphere of that radius. Beyond that sphere, the universe continues, possibly without limit. And in a universe that is very large or truly infinite, a vacuum decay event somewhere in the unobservable regions is not improbable over the full timescale of the cosmos. It may be essentially guaranteed. That thought has a very particular quality to it. Somewhere beyond what any telescope can see, beyond any signal we will ever receive, a bubble might already have formed. It might be expanding right now. It might be heading in our general direction, or it might be racing away from us forever. There is no way to know, not because our instruments are insufficient, but because the physics of information prevents any signal from arriving before the wall itself does. The universe is not just ending somewhere we cannot see. It may be ending in ways that are, by physical law, permanently invisible to us. That is not a horror film conceit. That is the logical consequence of special relativity applied to a quantum universe. In part 3, we are going to talk about why this might not be a coincidence. Why the knife's edge the universe sits on might be telling us something deep about the nature of existence, not just about particle physics. We will take the full picture apart, from the inside out, and ask the question that nobody has an answer to, but that everything in this video has been quietly building toward. 2 parts in, and something should have shifted in how you are carrying this. Not fear exactly, though fear is a reasonable first response. Something more like the feeling you get when a room you thought you knew well reveals a door you had never noticed. The room is the same, you are the same, but your understanding of where you are standing has changed, and you cannot unsee the door. That door, in this case, is the fact that the floor of the universe might not be the real floor. Every law of physics, every force, every particle, every form of life that has ever existed might be riding on a substrate that is one quantum accident away from being permanently overwritten. The door leads somewhere we cannot look, cannot reach, and cannot survive. Let us go through it. Something in the false vacuum story demands an explanation that most people do not notice at first. It is not just that the universe might be in a false vacuum, it is that the Higgs field appears to sit right at the boundary, not deeply inside the stable region, not deep in the unstable region, but right at the knife's edge between the two. The measured values of the Higgs boson mass and the top quark mass place the universe in the metastable region, technically stable, but only barely. Adjust the numbers within their measurement uncertainty in one direction, and the universe is comfortably stable. Adjust them in the other direction, and the vacuum is outright unstable and would have already decayed. The actual central values land right in between. Why there? Of all the possible Higgs field configurations the universe could have landed in, why does it sit exactly at the edge, rather than safely inside one region or the other? 3 possibilities have been proposed, and each one is stranger than the last. The most straightforward explanation is coincidence. The values are what they are. They happen to be near the boundary, and reading significance into that is a mistake. Many physicists take this position, and it is intellectually respectable. The history of science is full of apparent coincidences that turned out to be exactly that. The more productive explanation involves physics we have not discovered yet. There may be additional particles, heavier than what the LHC has found, waiting at energy scales we have not reached, that, when included in the full calculation, shift the boundary enough to move our universe comfortably into the stable region. The apparent metastability would then be an artifact of an incomplete theory rather than a genuine feature of reality. Finding those particles is one of the strongest physics arguments for building the next generation of accelerators. The third possibility is the hardest to hold in your head without your worldview shifting. Maybe universes that sit far inside the clearly stable region do not produce the conditions needed for the kind of complexity that generates observers. Maybe the proximity to the metastable boundary is connected to the same fine-tuning that allows stars to form, carbon to emerge, and life to arise. In this view, we find ourselves at the edge not because we were placed there deliberately, but because only universes near that edge produce beings who can look around and wonder about it. Universes far from the edge are either long since decayed or too different to permit consciousness. This reasoning makes physicists deeply uncomfortable because it feels less like an explanation and more like a mathematical way of shrugging. It says the universe is this way because if it were otherwise, we would not be here to notice. Which is technically true, but has the peculiar quality of explaining everything while predicting nothing. Given all of this, a reasonable question is, what has actually kept the vacuum stable so far? And the answer, oddly, is something we had nothing to do with: cosmic rays. High-energy particles from deep space have been slamming into every corner of the observable universe for billions of years at energies far beyond what any human technology can produce. The most extreme cosmic ray events hit Earth's atmosphere with energies tens of millions of times greater than what the LHC achieves in its most powerful collisions. Every neutron star, every active galactic nucleus, every region of violent astrophysical activity is running particle physics experiments at scales we will never match. And across all that history, across all that cosmic bombardment, the false vacuum has held. That is a meaningful data point. It tells us, quite directly, that the energy scales and collision types produced by natural processes, including everything human civilization could conceivably build for any foreseeable period, do not threaten vacuum stability. The vacuum survives things far more extreme than us, constantly, everywhere. Our place in the threat landscape is essentially negligible. What eventually ends this, if anything does, will be a random quantum event at a scale and a time scale that is completely disconnected from anything we do or do not do. That is reassuring. It is also, in a quieter way, unsettling, because it confirms that we are not the danger, but it also confirms that we have no lever, no influence, no ability to protect or extend the vacuum's life. We are passengers, not crew. Everything this video has covered, the Higgs field, the false vacuum, the bubble, the wall, the silence, points toward a question that does not have a scientific answer. Science can tell you how the universe works. It cannot tell you whether the universe should work that way or why it bothers. Here is the question. If existence is this fragile, why does it exist at all? There is no physical law requiring the universe to produce complexity. No equation demands the emergence of stars or carbon or cells or thought. The universe could have been, and most possible configurations of the laws of physics would have produced. nothing more interesting than a thin soup of radiation, or a brief burst of energy with no further structure. The fact that we got stars and planets and evolution and consciousness is not the default. It is the extraordinary exception. And yet here we are, in what might be a temporary pocket of metastability, watching the cosmos with instruments built from atoms the cosmos generated, asking whether the ground we are standing on is solid. We are the universe noticing, with equal amounts of wonder and horror, that it might be standing on the edge of something. There is something that does not quite have a word for it, in the fact that the false vacuum, if it is what the calculations suggest, has lasted long enough to produce beings capable of understanding it. The universe, by its own mathematics, is not supposed to be permanent. It is a temporary configuration sitting in an energy dip, waiting for the quantum equivalent of a wrong number to knock it loose. And in the time between the Big Bang and now, inside that borrowed stability, it produced everything. Every complicated thing that ever happened here, in the shallow dip, in the waiting. Maybe the transience is the point. Every structure is temporary. Every atom was once something else and will eventually be something else again. Every star is born from gas and returns to gas. The false vacuum just extends that logic to the universe itself. Even the stage is temporary. Even the laws of physics are on loan. Let us land cleanly, because dread without direction is just dread. The calculation that placed the universe near the metastable boundary was only possible because we discovered the Higgs boson and measured its mass. Without the LHC, without decades of theoretical groundwork, without thousands of physicists working across multiple generations, we would have no idea any of this was true. The fact that we can calculate the stability of the ground beneath reality is not a minor achievement. It is one of the stranger and more audacious things human civilization has managed to do. Knowing the universe might be in a false vacuum is a scientific fact, a data point, a piece of the map. Maps of dangerous territory are not reasons for despair, they are tools. What comes next is reducing the uncertainty, better measurements of the top quark mass, more precise determinations of the Higgs potential shape, and, if they exist, new particles at higher energies that would shift the calculation decisively. Either we eventually find that the universe is genuinely stable and the metastability was a calculation artifact, or we confirm it is real and understand it far more deeply than we do now. Either outcome is an answer. Both are better than not knowing. The universe might delete itself. Somewhere beyond our ability to see, it may already be doing exactly that, in silence, at the speed of light. Every structure, every story, every moment of grief or joy or curiosity might exist inside a temporary pocket of physics that will eventually be overwritten by something we cannot imagine. Knowing that, we keep going. We build better instruments. We write harder equations. We look out at the night sky with the knowledge that the sky itself is not permanent, and we look anyway. That refusal, that insistence on understanding even the thing that ends understanding, might be the most remarkable thing matter has ever done with itself. Either way, you watched this far. You wanted to know. That is enough. If this video shifted something, subscribe. Share it with the person whose brain needs a good breaking. Leave a comment telling me which part hit hardest. I read every single one. Next time, the big rip. The other way the universe might destroy itself, and why the evidence suggests it may already be in motion.